In this video, we're going to continue our journey to proving this nice inequality about the Ramsey numbers using the probabilistic method, but to do so, we're going to need to show this kind of weird inequality works. We need to prove that 4t is greater than or equal to 3. That's an important clarification. So prove 4t greater than or equal to 3. 2 to the power of t squared over 2 is less than 1/2 times t factorial times 2 to the power of t choose 2. That's lovely. Let's go ahead and prove that. This is going to be an induction proof. Since we're proving for t is greater than or equal to 3, our base case is going to be where t equals 3. In that case, we're going to have 2 to the power of 3 squared over 2. That's going to equal 2 to the power of 9/2, which equals the square root of 2 times 2 to the power of 8/2, or 4, which equals square root of 2 times 16. And then we can start doing some kind of fancy stuff. Square root of 2 happens to be less than 3/2, so we can rewrite that as 3/2 times 16, which is going to give us 3 times 8. And now we're going to rewrite this in a really funny way. That is equal to 1/2 times 6 times 2 to the power of 3. Why on earth would I write it that way? Because, well, that is the same as 1/2 times 3 factorial times 2 to the power of 3 choose 2. Remembering that 3 choose 2 is just 3. So, hey, look at it. We show that 2 to the power of 3 squared over 2 is less than, strictly less than, 1/2 times 3 factorial times 2 to the power of 3/2. So, we're done there. Okay. That's not a less than or equal sign. I'm going to box that instead of underlining it, because underlining it means something else. So we showed our inequality. Now, let's assume it's true for k. And prove for k plus 1, and show it works for k plus 1. That is, we're going to let k greater than or equal to 3, of course. Let 2 to the power of k squared over 2 be less than 1/2 times k factorial times 2 to the power of k choose 2. Then, let's start on the left side and see what we can get. Then 2 to the power of k plus 1 squared over 2. Well, let's start by just breaking that up. That's going to be 2 to the power of k squared plus 2k plus 1 over 2. So it's going to be 2 to all of that power. And I can rewrite that as kind of two pieces. I can write that as 2 to the power of k squared over 2 times 2 to the power of 2k plus 1. In fact, I'm going to write that as 2 to the power of just k times 2 to the power of 1/2. All of that's the same thing. So you could think of this middle term as 2k over 2 if you're not quite seeing it, but that's the general idea. And the reason we did all this is because at least one of these parts I can now play around with using my induction hypothesis. So I can say this is strictly less than 1/2 k factorial times 2 to the k choose 2. All of that times 2 to the k times, we'll write this as square root of 2. And let's just convince ourselves of something really quick. What's k choose 2? Well, actually, we'll get there later. I'm eventually going to ask myself what's k choose 2 plus k. Why am I going to ask myself that? Well, because, let's just reorder this stuff. This is really 1/2 times square root of 2 times k factorial times 2 to the power of k choose 2 plus k. I just reordered some stuff. And what is this k choose 2 plus k? Well, k choose 2 is going to be k times k minus 1 over 2 plus k. Well, that's going to be k squared minus k over 2 plus 2k over 2, which is going to end up being k squared plus k over 2, which, son of a gun, that's k times k plus 1 over 2, which is k plus 1 choose 2. So I can then rewrite this as 1/2 times square root of 2 k factorial times 2 to the power of k plus 1 choose 2. And we're almost in the clear. Because I'm going to make the grand observation that in this case k is at least 3, and 3 is bigger than square root of 2. So I can make this even bigger by replacing square root of 2 not just with k, but with k plus 1. Because that's clearly bigger than square root of 2. That's not what I had there. That's k plus 1 choose 2. And last but not least, I can combine that k plus 1 and that k factorial into a single k plus 1 factorial, and then multiply that by k plus 1 choose 2. So, and that's what we needed to show. We showed that 2 to the power of k plus 1 squared over 2 is less than 1/2 k plus 1 factorial times 2 to the power of k plus 1 choose 2, which is what we needed to show to prove our inductive hypothesis, or to prove the inductive step of our claim. So we showed that it's true for 3, which just, involved a little bit of algebra. Not even algebra. You could have just put this in your calculator, but, we don't have calculators, right? And then we, had to do some clever algebra down here to show the induction step, that if this inequality is true for k, then it's also true for k plus 1. And there we go. We were able to prove this weird inequality, which will definitely come in handy when it gets time to do our proof using the probabilistic method.